So we are now going to talk about a more formal or what is called axiomatic approach to probability theory. Um, so what is the plan? You may recall that we've already established a need for formalism and a need for a quantifiable way to understand nature, if you will. In particular, one of the example that we talked about was getting a nutty chocolate in the last segment. Okay? And what we want is a precise mathematical basis. And so we're going to provide just that. And I want to impress again, repeat myself a little bit, but impress again that it took about 300 and about 400 years to get to this level of formalism. And it's easy to assume that this level of formalism and clarity comes for free because someone has given it to you. But if you are interested in creating theory and new ideas that are going to last that long, it's important for you to learn how these things come about. Okay? So take some time to appreciate the clarity with which people have formalized this notion. So basically probability theory is just used to understand some natural phenomenon, and we're going to capture that by the notion called an experiment. And then on top of that experiment, the notion called experiment, we're going to lay down some probabilistic, a notion called the probability space. And on this basis, we will conduct the rest of our understanding of probability theory in this course and pretty much all of modern probability theory. Right? And we'll see some examples in today's segment. So let's start with this basic notion called an experiment. Okay. This is the very basis of probability theory. It's often not explicitly mentioned, but you have to realize that this is the very basis. It also goes by the term trial. What is an experiment? It's an activity, typically a natural phenomenon, a natural activity, but sometimes it can also be artificially done. So, for example, a computer can also perform something in a random fashion, and that also can be treated as an experiment. Okay. It's something that can be repeated as many times as needed, at least mentally speaking. Has a well-defined set of outcomes. So, this experiment should have a clear set of outcomes, and each time the activity is repeated, you can think of it as though nature is choosing one of the outcomes through some means. We don't know. We are not going to get into how nature behaves in specific terms, but we're just going to assume that nature is going to pick one outcome, and the set of all possible outcomes is called the sample space. Okay. So, given an experiment, you will have to have a sample space, a non-empty sample space, and if the sample space is exactly 1, then the activity is called a deterministic activity. But if the sample space is more than 1, then it's a randomized probabilistic experiment. Okay. So, let us look at some examples, and this is going to be a repetition of ideas that you have already seen before. A coin toss is probably the most fundamental experiment that you can think of, and of course, its sample space is heads and tails. Okay. These are the two elements in the sample space. Throwing a die is another experiment with sample space ranging from 1 through 6. Okay. So, they are all things that you have seen, and connecting with the example that we discussed yesterday, you know, our sample space is one of two things, either a nutty chocolate or a non-nutty chocolate. Here's a more complex experiment. Okay. So, we're just going to put together a few experiments and create a new experiment. Okay. We can do that. So, now what we're going to do is we're going to toss a coin first. Okay. If the outcome is heads, we'll do something, otherwise we'll do something else. If the outcome is heads, then we'll roll a die. So, after we roll a die, we repeatedly pick a card from a well shuffled deck of cards until you get a red card. So, that is if the die roll comes up even. But if the die roll comes up odd, we repeatedly pick a card from the well shuffled deck of cards until you get a black card. Or if the original coin toss was heads, well, you pick a card from a well shuffled deck of cards, that is your outcome. If you didn't follow all the details, don't worry, because the point was not for you to follow all the details, but the point was to illustrate that you can put together smaller experiments in some interesting way and create larger experiments, where what is the outcome of this experiment, this complex experiment that is there on this slide. You have 52 cards, that is your sample space, and at the end you are drawing a card from this sample space, right. All the inner workings are what nature does, if you will. Okay. What matters is that the sample space of this experiment is the 52 cards, and you are going to draw one from that. And importantly, hope you see that the makings of an algorithm. So, look, the way we have expressed this experiment should remind you of an algorithms course, pseudocode, and that is exactly the point. So, any algorithm that we design with the capability of tossing coins is essentially an experiment. So, now the algorithm that we are going to talk about has at its disposal coins that it can toss, not for buying anything, but tossing. Okay. And based on the outcome of those coin tosses, it can make decisions, right. So, basically any randomized algorithm therefore is basically an experiment, okay. And you can define the if it is an experiment, you should be able to define some outcomes. Without looking at specific algorithms yet, let us look at what are some interesting ways you can come up with outcomes. The most basic way of looking at outcomes is whether your algorithm has arrived at the correct output or the wrong output. Now, this algorithm is tossing coins along the way and making lots of decisions, going in some random way. What if it leads to a wrong output? And that is a serious concern that you should have. Okay. So, you want to have if that is your concern, your outcomes that you care about will be correct output versus incorrect output. Okay, let us assume you have established that your algorithm is correct, or at least mostly correct. If you might be interested in the running time. Okay. So, is your algorithm going to be, and let us say at a high level you just want it to be able to execute in reasonable time, then you can still define the outcomes to be either efficient or inefficient. Okay. And if you want to be even more nuanced about it, you can look for some fine grained outcomes. Okay. So, an example context that we will be seeing in this course is that after you run an algorithm, you want to ask the running time been small, as in within O of n log n or not, and you want to then argue, and here I am going to use terms that I have not yet defined, but you might be interested in things like, okay, this has running time O of n log n that happens most of the time. So, the technical term is with high probability, that is what I have as WHP. So, basically any algorithm that you run with the ability to toss coins, you have to think about the outcomes and you have to reason about the outcomes. And so, you see how these outcomes naturally fit with our understanding of algorithms. So, if you have had a basic course in algorithms, all the questions that you talked about there can be phrased in this randomized or probabilistic way. Okay. That is the important insight that you should have. Now, we have defined an experiment. Okay. It is basically something that has outcomes. We want to now provide some quantification to these outcomes, okay, and that is where the probability space comes up. Now, you start with a sample space, and of course, if there is a sample space, that means there is an experiment from which this sample space is coming. Okay. The outcomes listed in the sample space are typically called simple or elementary events, but you can also define some more interesting events, allowable events, or just an event is basically any subset of this sample space. Give you a quick example before we move on. So, now let us say you roll a die. Okay. The sample space is 1, 2, 3, 4, 5, 6, but you can also define an event which is an even number, okay, and that is like 2, 4, 6. That is a subset of the sample space, and that is an event. Odd, even, any subset of the 1 through 6 is going to be an allowable event. And the set of all allowable events, we call it F. We are going to stop at this level for now. Basically, you have a sample space and a set of subsets of the sample space, and that is what we care about and call F. If you are interested in exploring a little bit more, what I would ask you to do is Google up these two terms, sigma algebra and measurable spaces, okay, and you learn a little bit more about the formalism that goes behind this. Okay. By the way, I am going to be posting these slides as we go along. So, just to let you know, so you may use that as a reminder to Google these two terms to get a little bit more formal understanding of what we mean by these things. Okay. Now, we can quantify them. So, now we define what is called the probability function. Basically, it is a function that takes as input one of the events, that is the subsets in F, and maps them to real values. Okay. This is the quantification part. So, any event that you can think of has a real value associated with it, and that real value tells you how likely nature is to choose that particular event. And now we come to the axioms. There are three axioms that this probability function has to obey, and that defines a probability space. The first one is basically a normalization axiom, basically a quantification. So, this probability that we talk about is at least 0. Also, the probability of the entire sample space, because the entire sample space itself is an event, if you think about it, and that the probability of that event must be a 1. And the third axiom is, now if you look at any set of pairwise disjoint events. So, now these are, remember, events are sets. So, you can talk about pairwise disjoint sets. If you look at pairwise disjoint sets and you consider the event obtained by taking the union of those events. So, this is the new event obtained by taking the union of all these other events, these events E1 through E1 and so on, E1, E2 and so on. Now, that has to be equal to the sum of the individual probabilities. So, these three are the basic axioms. They are very simple and very intuitive, help you helps capture the notion of probability, and the entire field of probability theory is resting on these axioms. So, it is as simple as it is, it is also very, very important to very clear about them. Okay. Now, let us look at some examples. So, what do we mean by so let's go back to this event, this experiment of tossing a coin. Now, what we are going to do to understand the notion of a probability space, we are going to impose a quantification, and we are going to do that by implicitly calling it a fair coin. When we call it a fair coin, what we are doing is for each of these outcomes, we are going to assign a value half. And because it is fair, they both have the same value, which means they are both equally likely. This is, of course, I am sure an experiment that you have performed, you know very well, but I just want to take these basic concepts that you probably already know, make sure they are well set well within the theory of probability. You can go to the next level. What if you toss the coin twice? So, what is the sample space? So, at least what is the cardinality of the sample space when you toss it twice? 4. Okay. And then one more question for you. So, can you think of some meaningful events that are not elementary? For example, if you think of this tossing of a coin twice, you can think of a non-elementary outcome. For example, both coin toss outcomes have to be the same. So, that would be an event that corresponds to either HH or TT, both heads or both tails. Okay. So, we are rolling 2 dice. So, now what is the cardinality of this sample space? It is 36. So, now we can think of some interesting events. So, E1, so this is the sample space, but events you can define it based on your requirement, right. So, let us think of a few events. E1 is the event that both are odd, E2 is the event that both are even, E3 is, let us say, the event that the sum is even, and that is, by the way, the same as the event E1 equal union E2, because if the sum has to be even, either both have to be odd or both have to be even. Right? E4 is the event that the product is even. Okay. So, The only way you can not have the product being even if is both are odd. So, basically it is a sample space minus E1. So, what we are going to do now is we are going to argue that the probability of E1 and probability of E2 are both 1/4. Intuitively it should already make sense to you if you think about it, but we will just work through it carefully. You can similarly work out E3 and E4. So, here is how we are going to work this out. We have two dice, die 1 and die 2 are going to be rolled, right. We are going to, and so there are a total of 36 outcomes. The let us look at the first die being odd. So, now this so you basically the events are marked in green. So, the outcomes which fall into this event that the first die is odd are marked as green. So, now there is another event, this is that the second die comes out odd. Okay. So, here if you think about it, I am showing that as these stars. So, you have these stars basically corresponding to these rows. So, now we are ready to understand what the probability of E1 is. E1 is the event that both dice are odd. Okay. And this means that you can only consider those events, those outcomes in which it is both green and has the star in it, and so on. Okay. And that is what I have marked here in this purple color. And now if you, and implicit in this is the assumption that all the outcomes are equally likely. So, now you can use the third axiom to just add up the probabilities of the individual outcomes that are marked purple, and you will get 9/36, which works out to 1/4. Should make perfect intuitive sense, but it is good to see this in the context of the well defined notion of probability space. So, with that we are ready to conclude this segment. Remember the last segment we left off saying we need a clear formal and quantifiable understanding of the likelihood of some natural phenomenon, and that is exactly what we have done in this segment. We formalize that natural something as an outcome of an experiment. Okay. And on that basis we have defined what is called a probability space, and it is basically an axiomatic approach in which we have defined the notion of a probability function, giving 3 clear axioms that it has to follow. And then we saw some examples and quantified them, and we have some understanding of how these things work now. Okay. So, in the next segment what we are going to see is an algorithmic example, okay? And along the way we will also learn a few more concepts in probability theory. So, thank you.